Hey everybody, welcome to another Bill Sky, the Assembly Guy. And we're really moving on here. What's the next thing we're going to do today? We are going to take a look at how to move data in and out of the CPU. This video comes after the variables video, and it's really great because you're going to actually see how to move the data in and out of the CPU. Now the CPU is the central brain. Memory is simply like short-term memory in your brain. But you need to move data into the CPU to do anything with it, to add, subtract, multiply, divide, any of that. And in fact, after this video, we're going to be talking about addition and subtraction, and then after that, we're going to be talking about multiplication and division. Very interesting instructions when it comes to the CPU. So let's get started. All right, so I'm going to go ahead and set up my project. Now I'm going to do this in 64-bit. You could also do it in 32-bit. But I'm going to do it in 64-bit just so we can see the very large values that we can move around. So I'll go ahead and extract it. I'm going to call this, see, this is what happens if you don't rename your projects. They just kind of take on these strange names. So 64-bit, moving data. And let's see how we're going to do. All right, so the first thing we want to do is we want to move simple literals. We want to move immediate values, literals, into a register. So if you remember from the registers discussion, we have all kinds of different size registers. So I can move into RAX, which is a 64-bit register. I can move the number 10 hex. Or I can move into EAX, which is a 32-bit register, I don't know, 123H. So these are immediate values right here. These are literals. I can also move into AX, which is a 16-bit register, I don't know, 55. I can move into AL, which is an 8-bit register, 32. Or I can move into AH, another 8-bit register, whatever I like. Now I can also, instead of moving decimal or hexadecimals, I can also move decimals. I can also move binary if I want. And I believe to move a binary number, you put a B at the end. So let's actually see if that's correct. It's been a while since I've done that, and it works out fine. So I can use a B to move binary values in. So that's moving literals in. I can also, which is a very common thing to do, I can also move a character. So the capital letter A, I can move into a 8-bit variable. Now remember, the capital letter A or any character that you see on your keyboard is an ASCII character, which means it has a numeric value, and then you can see the value of that numeric value, or that ASCII value. Okay? Now that is moving literals. Let's put a comment there. Literals to registers. Now let's take a look at moving between registers. How do I move one piece of data from one register to another? Well, let's say I finished doing a big calculation and I want to move the result from RAX into some backup register. I can say move into R8 RAX. So that allows me to move one register to another register. And let's build that to make sure it works. Yep, no problem. I can move into RCX R8. I can save and build that. Works great. Now remember, R8 and RAX and RCX are all the same size. They're all 64-bit registers. However, what happens if I want to move into RCX AL? AL is a lowercase, not lowercase, AL is an 8-bit register. Let's see what happens. We get an error. We get an error here because AL is so much smaller than RCX, it doesn't know what to do with it. So I'm going to show you a little trick. If AL contains an unsigned integer, I'm going to say movzx. We'll talk about that in a little while. And that works. So we'll be talking about movzx and movsx shortly. So that's how you can move data between registers. But they pretty much all have to be the same. They need to be the same size. Now, let's talk more about this movzx. I promised you we would talk about it. Let's talk about it now. Movzx stands for move zero extended. So you'll do a movzx for unsigned small to large move. And what that does is that it takes everything to the left, all of the bits to the left of AL, so any bit greater than 8 bits to the left, it just puts all zeros in there. So RCX will contain, in this case on line 36, it'll contain all numbers, all zeros to the left. And let's go ahead and do something about that. I'm gonna, oh, we already have something in AL, right? So we already have this guy right here in AL. So let's go ahead and debug this. Make sure it's made, and then let's debug it. And we're going to take a look at what actually happens here in the debugger. Now, this is the same on Windows and Linux. Nothing we've done here so far is different on Windows, so that should be good. Okay, so let's go ahead and run this. I put a breakpoint on line 34. I'm going to take a look at RAX. Now, RAX, we've got some data in AH, because if you notice up here, we moved 12 into AH. The 12 to the left of the 41 is AH, so that has the value 12 in it. And then the capital letter A is the ASCII value 41. And while I'm at it, if you want to take, how can you find out what the ASCII values are of characters? Well, I'm going to bring up my browser here, and I'm going to go to ASCIItable.com. And from ASCIItable.com, you can see all of the ASCII values. And ASCII values are basically those things that you can create on the keyboard. And let's find capital A. There's capital A right there. And capital A has a hexadecimal value of 41. It has a decimal value of 65. It even shows the octal value and the HTML code. If you're an HTML developer and you want a capital A, you would use ampersand hashtag 65, and that would print that number. You would normally wouldn't do that as an HTML developer. But so ASCIItable.com is a great place to take a look at all the ASCII values. All right, so let's see what happens. I've got 12 and 41. Let's step over. Now what we're going to do is in RCX, which is down here, which has 1241 in it, I'm going to movsx AL into RCX, and watch what happens. It overwrites everything to the left of the lower bit, of the lower byte. So movsx is great if you want to move something smaller into something bigger, as long as it is unsigned. What does that mean, unsigned? Well, let's take a look at our code. So I'm going to go ahead, we did the movsx. I'm going to go ahead and move into AL the number -12. Then I'm going to move ZX, RCX, AL. Then I'm going to move SX. Now, SX stands for move, sign, extend. What that does is it takes the sign bit, which is the furthest bit from the right. It goes all the way to the left. It's the most significant bit in that 8 bits in AL, and it's going to extend it into the rest of RCX, and that will allow it to maintain its negativity, its negative value. So let's go ahead and do that, RCX. And let's build that. And now let's debug it. And what we'll go ahead and do is we'll get rid of this breakpoint because we're not really interested in that. We'll put a breakpoint there. So let's run it. Okay. So what we're gonna do is we're gonna put a -12 into AL. You know what I'm going to do? I want to do something a little bit to make it a little bit clearer for you. I'm going to go ahead and clear out. We will learn other ways to clear the registers. Instead of move, you can use a thing called XOR. We'll learn that more when we get into more of the advanced commands. So let's go ahead and make that. All right. Let's debug it. All right, so we're going to move 0 into RAX first. Let's run it. Okay, so here's RAX down there. That's what we're going to be watching here. That and RCX. We're going to be watching that as well. So let's go ahead and clear that. I'm going to move -12 into AL. It's weird, right? It shows 244. That is the 2's complement of the number 12. The 2. If you haven't seen that video, go and take a look at it. 2's complement. What's it all about? So -12 is actually 244, or F4, or 11111000 in binary. Okay, so there we go. Now I'm going to step over, and what I'm going to do now is I'm going to move AL into RCX. So now we're going to be looking at this. Notice it's 244 in RAX. That's the correct -12 value that the computer represents. I'm going to look at RCX. and it's 244, but is the most significant bit of RCX now 1? Is it now a negative? Is it a negative number? No, it's not a negative number, because if it was, it would be FFF4 or FFFFFF4. That most significant bit hasn't been sent all the way over there. So let's step over, and here we go. So what happened? I said instead of movzx, which is what created that strange negative number that didn't have the sign bit turned on, I moved SX, which is right here, and what that did was that took the most significant bit of AL, which said it was negative, and extended it all the way over, all the way through RCX, and now you can see our decoded value is a negative 12, which is exactly what we meant it to be. Now there is no way in the debugger to take a look at just the AL register, which is why it showed 244. But if you take F4 and you take its 2's complement, you will get negative 12 out of that. All right? But in a larger register, you have to extend that sign. You have to extend that sign bit all the way over to the left. So that's why you would use movsx if you've got a signed number. If you have an unsigned number, you would use movzx to do that movement. All right, so that's awesome. Let's go ahead and take a look at some of the other things that you have to be worried about when you are moving data around. So what we're going to do now is we're going to move memory into registers. And Windows and Linux are a little bit different about that. You know, if you do things the Linux way in Windows, you're going to be pretty safe. If you do things in Linux the Windows way, you're going to have to make some changes. So we're going to go through all that. All right, so how do we move memory addresses over? Or how do we move data from memory? So let's go ahead and create some memory. Oh, I'm still in the debugger. Let's go into the editor. All right, so let's go ahead and create some data. So I'm going to create I'm going to say some byte, define byte 10H, some word, define word. Let's make that 11H so it's easy to find. Some, let's say some D word, define double. And let's say some Q word, define quad. Okay, so we've got our variables. Now how do we, or we've got our memory locations. So how do we actually do this? Move that data into our registers. Now I'm going to clear out RAX. So I'm going to say move into RAX 0. So how do we move data from a variable into a register? Well, you simply say move, the destination is on the left, comma, and then you say square bracket some byte. So what actually is happening here? When I say move the square, first of all, the square brackets around the variable name or the memory label means dereference it. It means go out to the memory and grab that data. If you don't put the square brackets around it, it's going to put the address of some byte into our RAX. And let's actually see that. I'm going to go ahead and build it. And let's actually see what happens when I do that. And I placed that at the top of my code. All right, so we're going to put all zeros into RAX, and now we're going to move some byte. Now remember, some byte had the value of 11 in it. Let's see what happens when we actually do it. It's got this big horrible 405036. That's the address of some byte. And if you want to bet me on that, let's take a look. 405036, I can go to memory and say 0x405036. I can right click and say look at bytes, and there's my 11. There is my 11 right there. That is some byte. So that is the actual address of our variable. Now that's going to be very useful later on in the course, but for right now we're not going to be messing with that. So if you don't put the square brackets around your variable in Linux, you're going to get the address. How would you do this in Windows? Well, in Windows, you can do it this way. No problem. It's compatible between Windows and Linux. But in Windows, there's also another way I can just put the name of the variable. And if you're a Windows only developer, first of all, you're crazy if you're doing Windows only. But if you're a Windows only developer, that's fine. Go ahead and do it that way if you want to. If your application is going to be converted over to Linux or Mac OS, you definitely want to use this. It's compatible. I like the most common way. I like the most transferable way to operating systems. So I always teach it and I always do it that way. All right. So now we put the square brackets around it. Let's go ahead and make it. Let's debug it. Let's run it. I still have the breakpoint there, so we're going to move all zeros to RAX. And now we're going to move some byte to RAX. And what in the world is this? Just some huge, big, ugly number. Why? Why did that happen that way? Why isn't there just 11 in RAX? Well, the reason for that is because when you start moving data from memory into a register, it starts at some byte, and it fills the register with as many bytes as that register contains, starting at some byte. So it actually started at some byte, and it moved 8 bytes of data, starting at some byte. So it moved 11, then it moved 2222, then it moved part of some word. So that memory is all contiguous, so it moved it until it filled up RAX. And we can see that actually, we can demonstrate that again. And if we look at RAX, what's it got in it? 4, 4, a whole bunch of 3s, 2, 2, 2, 2, 1, 1. If we go look at some byte in memory, and if we right click and we say, I want to view it as 8 bytes, that number, 443, that's exactly what's in our register RAX. So you have to make sure that you put the right amount of data into the register. Otherwise, you're just going to get this huge, ugly number. So how do we do that? Well, remember the movzx? So I can say movzx. So I want to zero fill up RAX, but I want to move zx starting at some byte, a single byte. Starting at some byte. So and it's going to fill the rest up with zeros. So let's go ahead and debug this now after we built it. We're going to run it. Let's look at our registers. There's RAX. We're going to be looking at that. And now RAX has 11 in it, because we said move that data, move a single byte starting at some byte into RAX. All right, great. Now, another way you could do this, instead of moving it into RAX, you could have just moved it without the ZX. You could have just moved it in AL. And because AL is 1 byte, it's only going to take a single byte starting at some byte, and it's going to move that into AL. And remember, if you take a look at our registers video, AL is the very lowest number of bits in RAX. So it's just 1 byte, it's going to put it in there. Now, how would this work on Windows? Can we do this exact same thing on Windows? Well, on Windows kind of helps the developer, but it's Windows only. It actually teaches you less. So let's take a look at this funny little thing about moving memory into the CPU on Windows. Hey, welcome back. So what we're looking at right now is we're looking at a Windows 11. We got a Visual Studio 2022 64-bit assembly language application all set up. And what's really cool about this is that I just copy and pasted from the Linux into the Visual Studio. And watch what happens when I build this thing. Now, the reason that this happens is because I thought about Windows while I was doing the Linux and vice versa, so they're compatible. So without making a single change to the code, it just works. So actually, it doesn't work. It assembles and links fine. So let's take a look at some of the differences. So if I go up here and I say RAX instead of AL, so I'm not specifying a size and it's too big, Windows is kind of nice, because what happened in Linux is that it started at some byte and it just started taking all of the data. If you remember, we saw something like all of that data put into RAX. But on Windows, it did a little bit of a favor, in the developer a favor. It said, hey, some byte is just defined as a byte. So it's doing size checking for you, which is kind of nice. And it said that it just couldn't fit into RAX. So that's the situation where you might want to say something like a byte, but this is where Windows differs again, is that that's invalid syntax on macro assembler. So you can't put that byte there on macro assembler. So in this case, if you want to do this, you have to say movzx. Unless, of course, that some byte is a signed number, then you would move movsx. So if I go ahead and do that, it assembles okay. Now, what really should you do here? The preferred way is just specify AL. And since we've zeroed out RAX already, the movzx is just extra latency on the instruction. And latency means the amount of time it takes the instruction to execute. And so this is actually probably much more efficient doing it this way. Unless, of course, we take away this, then the movzx to RAX would probably be okay. Okay, back to Linux. One of the last things I want to do is talk about memory addresses. Now, we actually saw that a little while ago. And what I'm going to do is, I'm just going to demonstrate it again, and then I'm going to show you the little difference with Windows. So now, memory addresses are very important. They're pointers. If you've taken a C or C++ class, just about everything is set up with memory addresses. So you definitely want to make sure that you understand about how to use memory addresses. Now, where do you put memory addresses? Where do you put pointers in an assembly language program? Well, you have to look at the size of the word. So in this case, we're using 64-bit. So 64-bit memory addresses are going to be produced. If you're on a 32-bit operating system or your 32-bit project, 32-bit variables are going to be needed. So if I want to create a pointer, I don't know, some pointer, because I'm on a 64-bit, I'm going to say divide quad, and I'm just going to put, I don't know, 0. On Linux, it would probably be better, reserve quad, 1, and don't put it in there, because you don't need to initialize it, so we put it in the BSS section. So let's go ahead and get the address of our byte and our word, see how that works. So on Linux, it's very simple. You simply say move, and I like to use RSI because it's an index register, RSI, and just say some byte. That will produce a 64-bit address. Then I say move, and this is putting data back into memory. I then say move some pointer. We dereference it in Linux. We dereference the variable name to make sure it goes into the memory location, RSI. So that's putting data from a register into an address. Now you can do the same thing with any, let's say if we want to put into some point, or no, let's not do that. Let's put it into some keyword. If we want to store what we did in RAX, let's say we did a bunch of calculations, we want to move that into some word, we simply do it that way. So we dereference the variable. Now in Windows, if you want to move data from a register to a variable, you don't have to put the square brackets. However, if you do that and you move your program over to Linux, you're going to have a whole bunch of syntax errors. Or not syntax errors, you're just going to get a whole bunch of problems. So if you use the square brackets, you're common across all the operating systems. All right, so let's take a look. Now, before we actually do the demonstration, if on Windows, you might want to do something like this. So this would be a Windows version, or the Windows method. You would say move into RSI the offset of some byte. So that will move the address. You have to use the word offset in Windows to say offset means get me the offset address. Get me the address offset from the beginning of the segment. Give me that address of some byte and put it into RSI. And then you could do the same thing. You then say move into some pointer, RSI. Now this won't build on Linux because there is no such thing as offset. We have a problem here on line 35. It just doesn't know what that offset is. but that's the Windows method of doing it. So let's go ahead and build this and do a quick demo, and I think we should be done with this section. Okay, let's debug it. Let's set our breakpoint. That's perfect. Okay, so we're going to be looking at RSI. So we're going to, because we don't have square brackets, it doesn't dereference it, it just grabs the address. So let's step over. That's the address, 405.836, and as I showed earlier, 405.036. So if I say 0x405.036, we're going to see that we're looking at some byte. That's at 11. And now if I want to put that into my pointer, let's go ahead and say ampersand some pointer. And if you remember, it's 405.036. I step over, I right click, and because it is 64-bit, we have to look at 8 bytes. There's my 405.036. So I was able to store the address of my variable into a pointer variable, in this case called some pointer. Now if we go back to our registers, we can see RAX is 0. So I'm going to move RAX into, so you can put any register in there. And then some Q word should now have 0 in it. And there's my some Q word 0. If you remember, some Q word had all 4s in it. So that's how you grab an address of a variable, put it in a pointer variable, or you can move data around back to memory. And the important thing to remember when you're moving data back into memory from a register is that you use the same size memory and the same size register to make sure you don't get overflow, make sure you don't screw up other memory. Very, very important. If you have a single byte that you want to put into a byte location, you have to make sure you use the part of the register that's only going to move a byte in there. Movzx and movsx do not work going into memory. They only work going into registers. So you're going to have to do a size juggling a little bit to make sure you have compatible sizes of registers to memory. And that's why, one of the reasons why for the general purpose registers have different sized sub-registers made up, so it makes that programming much easier. All right, so that's it. That's our demonstration of how to move data in and out of registers. What I would really recommend you do is get your Linux, get your Windows going, try it out, move different things into different registers, take a look at memory. This was a really good debugging demonstration as well, because we looked multiple times at the registers, we looked at them multiple times at the memory, and that's really the meat of assembly language programming, is being able to debug it. Back when I was learning assembly language programming, there were no such thing as debuggers. We had to do a memory dump of memory on paper, and then you had to sit there at your desk looking at the paper trying to figure out what the problem was. So you guys are really lucky to have debuggers. So hope to see you in our next video. I believe that's going to be simple arithmetic. See you then.